Good afternoon, everybody, and welcome to the NASA Social for the MAVEN launch happening on Monday, right here at NASA's Kennedy Space Center in Florida. I'm John Yemberg with NASA's social media team, and it's a pleasure to be here today with you guys. For those watching at home on NASA television or on the web, what is a NASA Social? What is this event we're doing right here? And simply, it's taking the online experience offline. And what I mean by that is you're taking, normally NASA would, for example, take a photo of the launch pad. Well, here, we're inviting people on our people on social media that follow NASA to come out to the launch, to come out to NASA Kennedy Space Center, take their photo of the launch pad, and tweet that out or post that on Facebook to their friends and followers. So we're reaching people that we've never reached before. We're reaching people's grandmothers, reaching people's friends, and may not necessarily be interested in NASA. So that's one of the things that's really awesome about it. I kind of like to think of our NASA Social guests as social astronauts. And what do I mean by that? Well, NASA, we send astronauts, humans, into space, and while they're in orbit, they can talk about their experience there, like what it's like to view the Earth from space, what it is like to be in microgravity. Well, we're inviting our social media people to come out, and they're experiencing things, too, that most people can't see. They're seeing behind-the-scenes access. They're talking to astronauts. They're talking to engineers and scientists, and they're getting this special access in hopes that they go out and communicate it to their friends and followers and reach a larger audience of people that have never been reached before. Today is the 4-year anniversary of our first launch NASA social media event we did here at Kennedy Space Center. And when we started it, we didn't know. We didn't know exactly what kind of reach it was going to have. We knew that people would take pictures of launch pads and meet people and talk about what they were seeing, but we didn't really quite grasp how it was going to affect people. And what I mean by that is we thought they'd come out, maybe take pictures and go home back to their lives. A lot of times people become uber space geeks after this. They become ambassadors for the agency. And I don't think we really quite anticipated that. And who are these people? Yes, there's huge space geeks here today. There's no doubt about that. But there's accountants, there's teachers, there's nonprofit professionals, there's social media experts, all here today helping to share the story of NASA, which has been pretty good so far. A lot of people have already seen the launch pad today. They've gone out to see some of our facilities and met some awesome people, and that's what's going to continue here today in this program. So if you think about it, it wasn't that long ago. Well, first, let me ask everybody here, how many here in this room have never seen a launch before? Show of hands. Keep them up for a second. It's a lot of people. And there was one woman earlier today, and we were doing introductions, and she said, during launch, I want to apologize, I might get emotional. And I wanted to tell you, that's okay. What we're doing on Monday is extraordinary. We're launching a spacecraft to another planet. And if you think about that, that is just amazing that humans can actually do that. You should get emotional. This is special. And the things that you're getting to see today and tomorrow and Monday, these things are special. And I'm glad you're here to do it. And if you think about it, it wasn't that long ago in the course of human history that Mars was just a little dot in the night sky that no one really knew anything about it. And after more than a dozen missions, we know quite a bit about Mars now. And one thing that we know is it's unhospitable to life. But was it always? We know that billions of years ago, the atmosphere was much different, that there was water on the surface of Mars. What changed? And MAVEN is going to help answer those questions. And to get us started to talk about it is the Director of Planetary Science at NASA headquarters, Jim Green. Jim?
Thank you very much, John. It's really a delight to be here. This is a rather historic moment for us. We're launching a spacecraft to Mars. Next slide, please. But we do have a number of spacecraft already at Mars. As you can see, we have a fabulous next decade. Currently operating on Mars are 2 rovers and 3 orbiters. The 3 orbiters are 1, Mars Odyssey, 2, Mars Reconnaissance Orbiter, and 3, an ESA mission called Mars Express. Down on the ground, unfortunately, Spirit is no longer working. However, opportunity is going great. Yeah, absolutely. Opportunity, as many of you know, probably everyone knows, but let me just take a minute. It was only designed for 90 days. It was only not designed for 90 days because our understanding of the atmosphere was that it was very dusty. And as a solar-powered mission, okay, we'll change. That's good. As a solar-powered mission, it needed sunlight. And as the dust filters down, lays on the solar panels, the power will go, the circuits will die in the extreme low temperatures that occur at Mars. So 90 days is what we thought we could get. But indeed, Mars's atmosphere, even today, is continuing to change the way we think about Mars. It's actually very active. We see dust devils. And these dust devils have gone around and they have wiped off the dust on the solar panels for both Spirit and Opportunity, charging up the battery and allowing it to go further. And in fact, Opportunity ran its 26-mile marathon and more, and it's doing fantastic. Right now, actually, it's finding a place where it's going to sit in an angle, about a 23-degree angle on a hill, because Mars is entering winter. And as the sun comes up and goes down low over the horizon, we want as much power on the panels as we can get. So Opportunity will have to winter over. Our other rover, the one we launched from Kennedy in November 2011 and landed in August 2012, just last year, Curiosity, is going strong. And it is powered by a radioisotope plutonium-238. Now that glows red hot, and we take that heat and put it in a system for which material sits on one side of it. It's a thermocouple. It produces a voltage difference, charges up our batteries. And so Curiosity actually runs off batteries. But the plutonium continually charges those batteries. Can run at day, can run at night, can be as dusty as it wants to be. And in fact, that's very important for Curiosity to be able to accomplish its mission, which is a Mars year. Now, Mars year is about 687 Earth days, so it's almost like 2 of our years. And for that, we needed to have radioisotope power and not use the solar panels like Spirit and Opportunity did. So those are what we have operating on Mars right now. What's our future? Well, our future on Mars is very bright. As you can see, the next mission is MAVEN 2013. The next opportunity for Mars is 26 months later. Okay? And these are opportunities that are very important. All the planets have to line up for us to be able to launch a mission and catch up to Mars just as it makes it around its corner in its orbit and be there at the right place at the right time. Now, to me, the best analogy is every time I watch football, someone throws that long ball. He throws it before the receiver is anywhere near it. But when they come together and they cross that goal line, that's what we do when we go to Mars, each and every time. And that's critically important for these missions to make it, of course. So, in addition to MAVEN, in 2016, we worked with the European Space Agency for a mission called Trace Gas Orbiter. But NASA also has a mission. It's called InSight. InSight will get down to the ground again. We'll bore some holes, and we'll plop down some experiments, and it will measure what's happening inside Mars itself. We believe Mars is an active planet. And InSight will tell us a lot more about how active it is. Why do we believe that? Because from orbit, we see avalanches going on. We've caught them with MRO. Material flowing down mountains. Something is shaking Mars. That's what we believe is happening. There's Mars quakes going on. That's really exciting. Maybe Mars is not the dead place we thought it was. Every time every one of these missions go, we learn so much more about them. And InSight's going to take advantage of that and learn about that. If humans are going to go to Mars, and that's what they're going to do, that's our destiny. Okay? We have to leave this planet. Then we need to know everything about where we're going as possible. And that's why our science missions lead the way. That was true during Apollo, and that's true during today even. So InSight will make those measurements down on the ground. After that, in 2018, is another rover, European Space Agency. We're teaming with them. This is their rover, and it's called ExoMars. Fabulous little rover. We have a small part of one of the experiments that are on it, and we're also working with them in other ways for that mission. But then in 2020, we're going to take everything we've learned about Curiosity in terms of how to take a 1-ton vehicle and sit it safely down on the ground of Mars with a whole new array of instruments. And that's our 2020 rover. We haven't named it. We've just started to plan it, and the plans are coming together really well. Next slide, please. So here's Curiosity. A lot of people ask me, well, what's Curiosity up to? What's happened in this last year? Now, this is a selfie. This is not a fake, okay? With its high-resolution camera down on the arm, Curiosity took 54 images, okay? And sent those back, and we stitched them together, created the selfie, and, of course, probably put it on its Facebook account. But in any event, it's out in the web. You can easily get it. In fact, you can even see some of the little images that were used to put it together. Curiosity is going great. It is tremendously healthy. And in that year, these are some of the things that we found out about Mars. Curiosity has landed in an ancient riverbed. Water, and a lot of it, flowed in this area for tens of thousands, perhaps millions, maybe hundreds of millions of years. For liquid water of that volume to be able to exist on the surface, the atmosphere of Mars would have had to be much more extensive. Right now, the atmospheric pressure on Mars is about a tenth of what it is here on the Earth. But then, maybe 3.5 billion years ago, it was much more extensive, allowing the water to exist in a liquid phase. Pretty spectacular. Not only that, Curiosity has some of the most sensitive geochemical measurements we've ever put on any planet. And those instruments are telling us that the atmosphere has changed significantly over that time. We do that by measuring certain gases. One gas we love to look at is argon. And there is a little argon in the atmosphere of Mars. There's argon in our atmosphere. We see argon in the sun. We see argon in Jupiter. So argon has been everywhere in our solar system when it collapsed to form our planets. So what does it tell us? Well, there's two types of argon. There's argon-36 and argon-38. Argon-38 is heavier. And so when we measure argon, we want to measure the ratio of those two, the heavier to the lighter, or rather the lighter to the heavier. And we know what it is on the sun. We know what it is at Jupiter. We know what it is on the Earth. But what is it at Mars? The sun, the Earth, and Jupiter all have the same ratio of argon. But on Mars, it's much less. That means the lighter argon has left. It was there, had to have been there. And that means the atmosphere changed. That all fits well. The atmosphere went somewhere. The water is no longer there. It evaporated. We can't have liquid water in a place that we know liquid water was at. And in fact, now we understand even some of our older observations. When we flew by Mars with our early mariners and we saw the craters, yeah, we were depressed. It looked more like the moon. But when we saw how big those craters were, we realized Mars has a deficiency of smaller craters. They're not there anywhere near the extent that they are on the moon. Why? Because it had an atmosphere that was hefty And when those objects came in, they burned up, and they didn't cause craters. Now that fits too. So that's what Curiosity is telling us so far, and it has a lot more to tell us. Next, let's see the movie. So what is Curiosity doing now? Well, in addition to making some stops along the way, it actually is heading towards the very large mountain called Mount Sharp. But every once in a while, it will look up. And what is it looking for? Well, it's looking for MAVEN. Why is that? Because our rovers depend on our orbiters for communication. Our orbiters are the relay that allows data from the rovers to come back to the Earth, and for us to communicate to the rovers, we go through our orbiters. So in addition to having MAVEN follow up and understand the processes of how that atmosphere changed so radically in the last 3 or more billion years ago, it will be important for us because our orbiters are old and we need to refresh our communication. And that's another important part of MAVEN. Here MAVEN is, they're doing a solar array test, getting ready for it to go. Where's MAVEN right now? It's sitting on top of the rocket. Our Atlas ULA friends have done a fabulous job rolling that rocket out. It's sitting on the pad. MAVEN is at the last location here on Earth, bound for Mars. That is our next step, indeed. Now, when I look across here, I see a lot of people from the Mars generation. Okay? What do I mean by that? Next slide, please. This is what I mean. Now, not too long after Curiosity reached the surface, took a lot of shots. In fact, the mountain it's going to, Mount Sharp's in the background. And this was late in the day, of course, and there's its nice shadow. And we post everything. Someone from the Mars generation, looking into the future, saw what it was like and posted this. And when I saw it, I got it. Okay? Why? Because when humans go to Mars, this is what the shadow they will cast. They will have sleek suits. They will communicate with their rovers. They will have tools. And they will have their pet dog rover right next to them. And that's how we'll explore Mars in the future. Thank you very much. I think I got some time to answer any questions you might have.
Yeah,
is that
we got
right?
about 2 to 3 minutes.
All right,
so.
great.
Couple of questions. Who's up?
Yes, ma'am.
Hang on for the mic.
Thanks, Jason. Hi, I'm Kat at Kat Robinson on Twitter. I have a question. What are some things that you're hoping that MAVEN, with gives the atmospheric changes, will tell us about what might happen to our atmosphere here on Earth?
Yes, right. That's really good. I have to tell you, I'm a magnetospheric physicist, okay? That means I love anything and everything that had or has a magnetic field. And Mars had a magnetic field at one time. We know that. It's trapped in the rocks. But it no longer has an intrinsic magnetic field like the Earth. Now that, I believe, has helped this planet survive. That magnetic field, as our ionosphere evaporates into space, holds it tight and pushes away the solar wind. Mars doesn't have that. But one day, our field will go the way Mars' field will. And one day, we will be in an environment where we will have to face the solar wind without our buffer. So it tells us a little bit about the physics and the processes that occur that allow our atmosphere to hang close to the Earth and be battered in the solar wind and survive. Next question. All right. Yes, ma'am.
Tanya Harrison at Tanya of Mars on Twitter. I'm wondering, this is the first satellite that we've sent to Mars without a camera on board, and I'm wondering what the rationale behind that is.
Okay. It actually does have an imager. it has a ultraviolet imager. And so when the spacecraft, MAVEN, sits out at its apogee, or its apoapsis, its furthest location, it will scan the whole globe. And it will not take images of the surface like all our others do. It will take images of that atmosphere and how it interacts with the solar wind and how it changes over time. And they will be first-of-a-kind, beautiful images. Take my word for it. Where's our next mic? Wherever you got it. Okay.
Hi, my name is Patrick Ford. My Twitter handle is @PatrickMartian. A little bit about the apoapsis and the periapsis. My understanding is that it's going to dip into like 80 miles. So what is the projected lifespan of MAVEN, and can you expect to learn a lot in that given time span?
Okay, so the spacecraft engineers will be able to answer all the fuel and kind of questions for lifetime. But we expect MAVEN to survive one Earth year. 365 days. And we expect it to dip into the atmosphere. Now, that's really important. So when it's close to the planet, it actually is in the upper atmosphere. So it goes through the atmosphere and then ionosphere and then back out into the solar wind. And that's where we see each of those regions and how they interact together. So let's talk a little bit about the physics. A planetary atmosphere is something that is neutral gas. It's not ionized. The sunlight ionizes some of that gas, strips away some electrons, and we call that the ionosphere. So the very upper reaches of Mars's environment is its ionosphere. And that's the place that first hits the solar wind that will get stripped. So by dipping down in the atmosphere and coming back out, we'll see everything that is being forced into the ionosphere from the atmosphere and how that ionosphere interacts with the solar wind. Perfect mission to do that.
Fortunately, we're out of time. Thanks, Jim.
Come
really
on, give me a break.
Here.
All right, thank you very much. Enjoy the launch. Go MAVEN.
Thanks again, Jim. Our next panel consists of Lisa May, the MAVEN program executive. Lisa, you'll see she's wearing stylish glassware. We also have Kelly Fast, the Mars program scientist at Goddard Space Flight Center. It's like a runway here. It's really exciting. You got to do the walk, right? We also have Sandra Kaufman, MAVEN deputy project manager. And finally, we have Chris Waters, system design lead at Lockheed Martin. Let's give a round of applause to our panel.
All right, so they're each going to take a few moments and talk to you about who they are and what their role in the project is, and then we'll open up the floor for questions here. So take it away, Lisa.
Hi, folks. Thanks for coming. This is terrific. I am Lisa May. I'm the MAVEN program executive and also the lead program executive for all of Mars at NASA headquarters. And I just first of all want to say, okay, glass. Okay, glass, take a picture. And also, you can find me at LD May. Very simple. Yeah, so you can feel free to follow me. Mostly tweet about MAVEN, but really it's just my account. So officially speaking, I have been with MAVEN since before it was selected. One of the things you should know about these missions, it's a PI-led mission. Some of you may have seen or heard about or met Bruce Chakosky, the principal investigator of MAVEN. And what that means is NASA put out a call not for a space mission. NASA put out a call for a science investigation at Mars. And so what we do is we select a principal investigator who says, this is a great science investigation, and I have to find a team, and I have to pick the instruments, and I have to figure the budget and the schedule and everything else. And wait, I was a scientist. Okay, I still have to figure out a schedule and a budget and pick a team and figure out hardware and who to go with, and it's a very big competition. And so I've been with this since 2006, at the very first stage of the competition, since before we selected MAVEN as the Mars Scout that's flying this year and, well, next week to Mars. What I do at headquarters, you'll perhaps see this on Twitter here and again, is the engine for NASA and innovation and research for us is both Congress and the administration. They give us direction, they give us money, and tell us what to do, and we implement that on behalf of, well, ultimately on behalf of all of you. But the rubber meets the road for the people who do things, and you'll talk to some of them in a second. And the rubber meets the road at industry and at universities and at NASA centers and government agencies. And that's where the real hardware gets done and the real hard work. Something has, so you've got the engine, and you've got the rubber meeting the road, and there has to be something in between to keep the gears from grinding. And that's what we at NASA headquarters really do, is we make sure those two things mesh, and progress continues, and the journey to Mars is smooth. And I'm going to give you over to Kelly Fast, who's the program scientist at NASA headquarters for MAVEN, and a whole bunch of other things.
Thank you, Lisa. All right. Okay, oh boy, she's so with it. This is fantastic. I'm Kelly Fast. I've been tweeting. Oh boy.
Which also means you're on
Kelly
Facebook.
Fast. I'm serving as the program scientist for MAVEN, and it's such a pleasure to be here to be a part of this mission that, even though other missions have studied the atmosphere of Mars as part of their overall mission for looking at the surface and the atmosphere, MAVEN, it's the first time that we have a mission that's dedicated to studying the upper atmosphere of Mars and the interaction of the sun with the upper atmosphere, and to try to answer that question, what in the world happened to Mars? You heard from Jim Green about how there's all this evidence for water in the past being on the surface, which would have required a thicker, warmer atmosphere. What happened? And so the scientists are just so thrilled and just cannot wait to see what's going to come in from MAVEN to start answering those questions. What happened? And so it's been my privilege to work with the science team at NASA headquarters. I'm the keeper of the Level 1 science requirements, but I've also had the incredible privilege of being able to oversee a process to bring some more people on the science team. Scientists, in all their research, they have to, in order to get funding to support it, they have to propose what they would like to do. And then a team of peers, of other scientists, they evaluate it, they rip these concepts apart and put them back together again, and eventually what floats out unscathed has the potential to be selected. So we brought more scientists on the team to get the most science out of this mission. And I do that with some other programs not related to MAVEN at NASA headquarters, and I'm also responsible for the NASA Infrared Telescope facility out in Hawaii. So it's just been a pleasure to see things from all aspects at NASA. But right now, what we're here to see is MAVEN launching, and we're just so thrilled about it, and I am so privileged to be here. And to tell you even more about that, I'm going to pass this along to Sandra Kaufman.
Hi there. I'm Sandra Kaufman, and I'm going to say it in Spanish. Sandra Kaufman, just in case. I am the Deputy Project Manager for the mission. I work at Goddard Space Flight Center. We have been managing the mission since its inception. And I work directly with the project manager, David Mitchell, and I'm responsible for looking across all of the aspects of the mission, working with all the partners, working with the headquarters. So it's been a big job for Dave and I to really keep things moving, coordinating, working with the independent review teams. And one tidbit, we have been counting reviews since the kingdom come, since things began, and we are up to I think it's over 200 reviews. Maybe I can count this one too. But, you know, we are constantly being reviewed and assessed. And, of course, we are constantly reviewing and assessing all of the partners. The LASP that provided the IUVS instrument, one of the instruments, the Space Sciences Lab in Berkeley, at the University of Berkeley, they provided 6 instruments for us. And, of course, Goddard provided 2 of the instrument packages that we are going to fly on MAVEN. So this has been an exciting moment for all of us, and we are thrilled to be here on L-2 and counting. We just can't wait to see that rocket go on its way to Mars. Of course, that's just the beginning. We still have to get to Mars, and the trip to Mars is going to take 10 months, as you know. And on our way to Mars, we're going to be checking things, calibrating instruments, making sure that everything is working as expected. And once we get to Mars, it's going to take us about a month to, again, do systems checks and make sure that everything works properly. And we are going to have 1 year of science operations that we can't wait. So this is just the beginning of the end. We still have to get to Mars. And like my boss says, I hope the launch is great. I just hope we get to Mars too. And and I'm going to pass the microphone, I guess, to Chris Waters, who is the spacecraft manager for Lockheed Martin.
Thank you. I am Chris Waters. I'm the system design lead for Lockheed Martin. So my job on MAVEN was to coordinate the engineering effort across all the engineering teams and basically arbitrate the various disciplines as we worked through design trades and decisions, and make sure that when it all came together, we had a spacecraft that could accommodate the needs of all the payloads, meet our science objectives, and still stay within the constraints we have for things like mass and power and data return. So it's been a tremendous challenge and one of the best jobs I've had in my career. And here it is. I think everyone's probably seen a lot of the pictures of it, but just to give a quick overview of the spacecraft, the main bus is about a 7-foot cube, a little over 2 meters on a side. And that hosts, it's a composite structure, hosts all the typical avionics systems, a lot of which we inherited from our previous missions. Probably the biggest aspect that jumps out at people is the gull wing solar array design, the 20-degree cant. And I think the common perception, or the most intuitive one, is that we have some operations that take us deep down into the Martian atmosphere to the point where we need to rely on aerodynamic stability to hold the spacecraft in a stable attitude. But there's actually another reason, and I think this one, to me, is one of the cooler ones because it was one of the biggest challenges we had, and that MAVEN actually relies on sensing the atmosphere every orbit. And when we're in our nominal altitude, the drag we get is about 1/4 of an ounce. You think about that, that's 3 or 4 dimes placed on top of a 3,000-pound spacecraft. And we have to sense that and adjust our knowledge of timing in the orbit every time we go through. So we actually needed the cant on the solar arrays to help cause some torque as we pass through the atmosphere in certain attitudes. So that's one of my favorite aspects of the mission. And I guess the other one that jumps out is the deployed platform there, the Articulated Payload Platform, or APP. And the reason for that is that we have a whole suite of instruments, and they're looking all over the place. Some of them are looking at the sun or relative to the sun. We're looking perpendicular. All those are hosted on the body because with the solar arrays, we're normally going to be pointed at the sun. But then we have 3 instruments that want to look at Mars or relative to Mars, maybe out at the limb. And we need to be able to articulate and point those around. So we had to split those out on a separate platform that's on a 2-axis gimbal. We can get into more, I guess, if you have any questions. But I think for now, we'll just open it up.
Yeah, we can take questions now. Remember to keep your hand raised and start over here.
Hi, I'm Zach McCauley. My Twitter handle is at Arma358. This is for Chris. I know that they do deep dip maneuvers for MAVEN. How much more is the drag on the actual spacecraft?
When we go into deep dips, we're lowering down about 25 kilometers. So we're normally about 150 kilometers above the surface. We'll drop down to 125. I mentioned the nominal drag is around 1/4 of an ounce. When we get down in the deep dip, it's more like 1/2 pound. So it's still not significant, but relative to the normal orbit, it's quite a bit.
Hi, this is for the science team. Casey Friels at Casey Friels on Twitter. What's your working theory on where Mars's atmosphere went? Large impactor, something along those lines?
Well, the main part of the MAVEN mission, looking both at what's coming in from the sun and looking what's going on in the atmosphere, in the upper atmosphere today, are to look at processes that lead to escape of the atmosphere that don't involve a large impactor, but just something that's even going on today. The Earth, as Jim had mentioned, we've got this magnetic field, this large magnetic field that helps shield us from the barrage of particles coming in from the sun. And Mars, there's evidence it had it at one time, and then for some reason it doesn't have that now. Maybe things cooled, maybe there was an impactor that affected that. But for the atmosphere itself, once that shut off, once that magnetic field shut off and stopped protecting the atmosphere, that barrage from the sun can start interacting with the upper atmosphere more, and through different processes, chemical processes, through collisional processes, atoms and molecules in the atmosphere gain the energy to escape and leave. And over time, and with a different activity of the sun and all, eventually that can lead to the atmosphere being stripped away. And the reason is also some of the water in the atmosphere from the past could be down in the rocks, but there's really not enough evidence of that, and so that's why the other way it could go is up. If it didn't go down, it could go up. And so by looking at what's going on today in the atmosphere can hopefully take that and track it back in time and see, does that make sense that those were the processes that led to the escape of the atmosphere. So it's really more this kind of constant barrage that's probably responsible, but that hasn't been quantified, and that's what MAVEN will get to do.
Good afternoon. Ryan Lores, at Ryan Lores. I actually have two questions. The first one is for launch. I know for the STS, the percentages have to be really high for it to actually go up. But with the 60%, how much leeway is there for this actual Atlas V? And then the second question is pertaining to India's MAVEN mission that left, I think, a few weeks ago. I know we're supposed to be there about 2 days prior to it. How close are we going to be when we pass that spacecraft? Thank you.
So I might let Chris take the launch constraints question, and I'll talk about MAVEN.
Okay, yeah, there's been much ado about the predicted percentages on Monday. Our ULA friends assure us that that's a fairly conservative number, and you have to remember, they think of it in terms of a percentage of probability of having a violation of the launch constraints during the window. So there's a 40% possibility, but all we need is one shot somewhere during that 2-hour period. So they're still very confident that we have a good opportunity coming up on Monday.
And if you hadn't heard that we do have multiple opportunities throughout the 2 hours. So it's not as if we don't go right at 128, then we're done for the day. And with only a 40% probability of violation, I'm still planning on seeing a launch Monday.
Time to leave the planet.
As for MOM, yeah, they did launch on November 5th per their plan, and they are conducting their orbit-raising maneuvers here at Earth. They're using a transfer orbit to gain enough energy to go to Mars. And in fact, MOM is being supported by the NASA's Jet Propulsion Lab, the folks who do the DSN, the Deep Space Network, as well as some of our navigation and trajectory folks have been working with them for quite some time. So we will be quite aware of their progress towards Mars, and they will be quite aware of ours. And in fact, you know, what you may or may not know, and I'm going to actually exceed my own knowledge here because I don't do trajectory design, but we do design our trajectories, and we design our times for leaving and for arriving. And so in working with them cooperatively for months, we know we're going to be separated in time. It's not like it's a race to a finish line and a possible collision or something at Mars. Also, their orbit is quite different. It's very, very eccentric. I mean, ours is elliptical at 6,000 kilometer apoapsis and 150 kilometer periapsis, but theirs is something on the order of 80,000 kilometer apoapsis. So it's a very different orbit, and it's going to be exciting. Their primary goal is technology demonstration, showing that they are not just a spacefaring nation, which India has been for quite a long time, but also that they're a Mars-faring nation. There are some scientific instruments on there, and if they succeed in their goals and they get there and the instruments are operating, we'll be having talks with them about how we can collaborate in the future, either with these measurements or with other missions.
I'm going to add that my understanding is that we are going to get to Mars about 2 days before they get to Mars.
Yeah, we're the 22nd, they're the 24th right now, depending on when we launch and how the rest of their burns go. There are hands up. Yeah.
Hi, this is Teresa Barber. I'm president and CEO of Fairfield Index. And this is for all of the panelists. I'm curious to know when you were first inspired into sciences and engineering. And especially for the women, what would you tell young women or men, but young women especially, how to navigate into the careers like what you have had today?
So, Chris, I guess you can just take a nap.
Go ahead and start.
You want me to start?
Yes.
All right.
Sure.
Then I'll take my nap. For me, it's as far back as I can remember. My family's been into aviation. My grandfather was a pilot. My dad was a pilot. So I grew up around airplanes. I was born in Texas, and we had some friends that worked at Johnson Space Center. And we got to go in a couple of times with some behind-the-scenes tours. I got to see the Space Shuttle Enterprise come in as it was being ferried around. I got to go in and actually fly the simulator late at night as a kid, which was incredibly cool. And that's just everything as far back as I can go. I just knew I wanted to work in aerospace. So.
Well, my story is a little more complicated than that. I was not born here. I was born in Costa Rica. I was born and raised in Costa Rica, and I moved to the States when I was 21. But my story begins, and you're going to date me when I say when. I was watching Apollo landing on the moon, and Neil Armstrong touching on the ground, and I was 6 years old. And I was at that point, thrilled, and I turned around and I told my mother, I want to work for NASA one day. My mother just looked at me. My mother is a single parent and trying to figure, how to make ends meet. And, she just said, just study hard and apply yourself and be ready because you never know when the opportunities are going to jump. And the world turns around many, many times, and you never know, what will happen. So, I took that to heart, and I really, continued to study. And all my life in high school, elementary school, I wanted to find a way to work for NASA. And I tell you, I cried, my mother cried, and we all cried when I got my job at NASA, 22 years ago when I became a civil servant. So, of course, I had to come here, and I had to become a citizen to be able to work for the agency. And, not to bore you with details, but I'm here. So.
I'm sort of an odd case. I grew up in the Hollywood Hills, and I don't know how somebody who grows up in the Hollywood Hills becomes a scientist, but apparently my dad snuck me into the Griffith Observatory and lied about my age and into a planetarium show when I was too young to go in there. And then as a kid, I loved Space 1999 and Star Trek. Oh, boy. I wore my uniform to the movie. Okay. Yeah. Mm-hmm. They don't do that back east so much, but I do it anyway. I loved that, and I got a telescope, and I guess I got into this by way of astronomy, and you get this thing, if any amateur astronomers out here, you get aperture fever, because then you want a bigger telescope, and I take it outside, and yeah, in Los Angeles area, lots of bright lights. It's difficult to see things, but you could see the planets, and that's what I love to look at. And it was at the time when the Voyagers were going by, and so I just decided I want to go this route, and didn't have any reason to think I couldn't. And there was the question about women being involved, and yeah, it is different for women. And I just feel very fortunate the route I took. I mean, it wasn't a standard route. I ended up stopping my education for a while and had kids, and I was working part-time. I was really fortunate to have some other colleagues at NASA who let me have the flexibility to kind of do a lot of telework. And this was at a time, I got a kid in college now, so this is at a time when I always say I pioneered telework. But some of the best work I ever did was with a baby in one arm and typing with the other. But I think every woman has to find her own path and find that balance, because it is tough. And I'm a believer in that you really can't have it all. You have to make some choices, and every woman has to make the right choices, and then look for people who are willing to help work with those choices. And it's not easy, but it can be done. And I just feel very fortunate to be able to make it work. Okay. Oh, yes.
I feel old. My mom always used to say, you can have anything you want, you just can't have everything you want. And that you follow on with, I think it was George Carlin used to say, you can't have everything because where would you put it? So that all made sense to me as a kid. I was early on a math and science geek in school, and I went to, fortunate enough to go to small private schools. So I never got any of that pressure of girls aren't good at math or whatever, and getting really high math scores was great. I skipped a grade. I'm just young enough that nobody said go be a nurse or go be a science teacher, which is a great thing to be, but they said go be a doctor. Nobody said go be an engineer. I don't know why. I'm just old enough that engineering wasn't necessarily a career path for young girls. Nobody thought to tell me what one was. Now, mind you, half of my high school, I lived near an IBM facility, and half of my high school were IBM kids. So I know that the grown-ups around me knew what engineers were. And by the way, my father also built houses for a lot of Pratt Whitney engineers. Nobody told me what an engineer was. I had no idea. I go to school. I get to college. I have no idea what I want to major in. I think I'm pre-med, and I hated it. I completely hated it. I really did. So I bailed. I went and majored in what my best friend was majoring in, which was speech communication, and I worked in radio news. And I was an English grader for an engineering professor. Yeah, that's right. Any of you who've had technical classes where you've had a really hard professor, this guy, 50% of every paper, lab report, and project was grammar, spelling, punctuation, and ability to follow directions. And he hired a communications major to do the grading. They hated me. But I learned what engineering was, and I really learned to love it. I was also the only undergraduate major in speech communications at the University of Virginia taking calculus, physics, design, and programming languages as electives. So it was obviously where I belonged. I just didn't know it. It took me a long time to figure that out. And I thought, hey, I'll get a master's in engineering, and it turned out to be home. And it really did. And it took me a long time to figure that out. Now, there's a corollary to that is I grew up just south of here. And I saw, things launching in the sky as a kid and, played astronaut with my brothers. Never had any notion or desire to work in the space program. Never had any idea what an engineer was. And I sort of wandered into it in sort of a even more complicated way than Sandra. At least she knew what she wanted. But again, there was that sense of feeling at home. Once I got the engineering degree, how can you do that? You have a speech major. How can you get through engineering school? I was like, actually, this is easy. This feels like a relief to me because this is what I'm really meant to do. And the same thing as I wandered through a few different engineering jobs, and this feels like what I'm supposed to do. And so this is what I do. And really, if you're doing something and it feels like you're fighting yourself every single day, take one step to the side or one step forward or ask somebody something else or do something that makes you incredibly uncomfortable but sounds really fascinating. Or just accept the fact that you're really mad about what you're doing and move to something different because sooner or later you're going to relax into that place that's right. And it actually, frankly, doesn't matter if you're a girl or a guy or anything or an alien. I mean, it really doesn't matter to me because this is what I do. And by the way, I do a lot of by training, I'm a mechanical engineer, but by temperament, I'm a systems engineer. So I'm really all about setting requirements. What are we trying to accomplish? How well do we have to accomplish them? And one of my, I see some people in the room are going to cringe when I say this. One of my favorite things to do besides things are going to launch on Monday is proposals. I used to have my own company that I did proposals. And I loved it because there are so many requirements where you get to create something and you get to set the requirements that 7 years later somebody's going to launch off of a pad at Kennedy Space Center. So I really enjoy that. And it brings together both the communications and the engineering. I haven't regretted either for a second.
Hello, I'm Jim Edwards Hewitt, Redshift 42 on Twitter. We've gotten a sense of the kind of things you're looking for in the science, what you're expecting to find, and I know some of the past surprises from Mars missions have been finding evidence of abundant liquid water on Mars and the lack of carbon dioxide having been absorbed into the minerals. What would be surprising results from MAVEN?
Oh, boy, that's a good one. I guess it's just going to be, the reason we're sending this is because there's some idea of some of the processes that are going on in the upper atmosphere that lead to things like carbon dioxide eventually escaping up instead of down. But I have a feeling that once those things are measured, everybody's going to have to go back to their models and change everything. The team is working very hard right now to get models in place so when the numbers start coming down from the spacecraft, they can start chugging it and get some science out of there. But I have a feeling on the way they're going to go, oh, that's not what we were expecting, and they're going to have to go in and change their programs. And I can't put a finger right now on what exactly, that big surprise might be. One surprise might involve if there's some event on the sun that impacts Mars, that this will be, a chance to really study it well, and that might rewrite the books on some things. But a lot of it is, if we knew it, then why go? So it's going to be cool stuff.
I'm a science enabler, but one of the things that I think would be surprising, one of the things MAVEN's going to do after they've done all this crank turning and modeling and analysis and correlation of the current escape and the processes from the sun and the sun's activity, is they're going to look back in time and try to walk back and see what happened. Not what's happening now. It is very clear, and it is their first mandate to figure out what's happening now. But that process of figuring out what happened and what ancient Mars, or at least much older Mars, was like as far back as we can extrapolate with that data, I'm really looking forward to that. I think that's going to be a story that's going to be worth hearing when we get there. I mean, the primary data of what's happening now is fascinating enough, but I can't wait to hear the history story they're going to be writing.
Adam Holt, and I tweet at Adam Holt Writes. And my question for you is that, I think NASA's always had kind of this legendary determination and ingenuity. And so I was curious, what was one of the biggest challenges that you faced in putting the MAVEN on the pad?
Looking at Sandra.
We had many challenges along the way. Of course, everything since the beginning, since 2003, when the principal investigator and the couple of scientists met and decided that they wanted to do this, trying to get the money was a challenge. And then, trying to win the first science proposal, that was a challenge. And then, trying to get submit the concept report and be the winning proposal to execute MAVEN. And, of course, getting confirmed. And, once we start putting hardware together, I'll let Chris talk to some of the hardware things. But, throughout all of the processes, we've had issues with the instruments that we've had to replace parts. Right after we shipped the spacecraft to Kennedy, we had a problem with the RF card in one of the instruments, and we had to take it out of the spacecraft. We had a completed spacecraft delivered to Kennedy, and we had to take it off the spacecraft and ship it back to Goddard to fix it, and then ship it back to the Kennedy Space Center and reintegrate it. And we were hoping that all of that could happen smoothly and without any problems, and that's what we did. The team delivered. They worked, long hours overnight and shipped it back. Then, of course, the furlough was one of those things that, impacted us tremendously. We were very afraid that we were going to get shut down and miss our window of opportunity for launch. So we were able to get restarted. The lawyers and everybody got involved and trying to figure out, whether we could get it started. We lost 2 days. They restarted us again on October the 3rd. We only lost 2 days, and we were able to work a couple of double shifts in a weekend, and we recovered the margin and the schedule. And we are here today to, L-2. So it's been a long road and very challenging road, but we have a team that is, up for the challenge, and we've lived up to it. And we not only are delivering have delivered things on time. We're hoping that we will have a successful launch on Monday and get to Mars in September of 2014. And I'll let you talk a little bit more about it.
Sure. Every project has its own set of challenges. I mentioned one, the aerodynamics and trying to detect these tiny forces. That was more of an early concept to get us through the preliminary design and show that we had something that worked. And that was a huge challenge. And I think we have that one now well under control. The other one is that we have a requirement that the spacecraft will cause a change in the magnetic field at the magnetometer locations, which are these two triangular tips at the end of each solar array, of no greater than 1/4 nanotesla. Now that sounds like a small number. It's kind of hard to put into perspective, but I looked up on the web the other day that a typical household magnet has something like I think it's about 1 millitesla. So we're talking about 5 or 6 orders of magnitude less than your typical household refrigerator magnet. The initial concept for trying to knock that down is to push the magnetometers as far away from the spacecraft and all the noise sources as you can get them. But of course, the farther out they get, the harder it gets to be. Do you need to put it on a deployable boom? Do we increase the size of the solar arrays, in which case, as they go through launch, it gets to be like a diving board, and it really starts flapping around. So we settled on the current design. And of course, as we got in through the integration, we had a few surprises where components came in and measured a little bit noisier than we were expecting. We found a heater circuit where we're trying to run the current through the heaters in reverse direction so they cancel each other out. We found that we had 2 that were wired incorrectly, so they were actually adding. We had to go back in and correct that late in the game. So the magnetics was probably one of the biggest challenges, technical challenges we faced through MAVEN.
I got one that the team faced that they're sort of alluding to is this is a cost-capped mission. Now, these competed missions, not only do you have to have a scientist who figures out what to do and gets selected and go through the proposal process, then they have to manage to a very tight budget. And when Sandra said, we had to get through confirmation, she sort of said that lightly. But that is the moment in a NASA project where the project and the agency look at each other eye to eye across the table and say, here are your level 1 requirements. This is what you got to do and how well you got to do it. And this is how much money it's going to cost. And not only do we agree to that amongst ourselves, we tell Congress, we tell the Office of Management and Budget, we tell the world, this is it. This is what this cost-capped competed mission gets. And this team has been a marvel of planning, performance, execution, being on schedule, being on budget. It was nerve-wracking for them, but no surprise to me. And look, I'm from NASA headquarters. I'm supposed to be the bad guy, right? No surprise to me whatsoever that when they were reactivated after the furlough, they did have to shut down. They did orderly shutdown, as they were required to do here at Kennedy and at Goddard, where they were reworking the instrument. But when they were reactivated, the actually says, we just did some double shifts and we got caught up. Within a week of having to turn everything off, start it back up, replan things, and deal with this problem with the instrument, they're back on their schedule. They're working 1 shift. And throughout the entire process, it's been one of the big risks is double shifts and extra people needed. And they've just been so good at planning and so good at making decisions early enough that they don't become giant problems. It has been a pleasure since we selected them for step 1 and have had to work with them through the second proposal and through the entire project. And it is the whole series of challenges that go with that. And they've handled them with grace and professionalism, and they've been terrific.
My name is Hampton Black. My question is, during transit to Mars, will the MAVEN have any ability to measure high-energy radiation SPEs similar to what we did on MSL?
Yeah, while we're in the cruise phase, some of our instruments will be powered up and looking. We won't be generally in the right attitudes or orientations for them to do their full science, but we will have several of specifically the particles and fields instruments powered up and able to monitor for those kinds of things.
Yeah, hi, Tom Balzamo. I tweet at tbalzamo. Thank you for having us here today. I wanted to ask, it's been mentioned several times already about the studying of the rate of changes in the atmosphere on Mars. What have you found in your research, or what do you expect to find with MAVEN, that would indicate those changes have been uniform throughout the history of the planet?
Well, that's a good question, because by studying the current state of the atmosphere, you're seeing what the current state of the atmosphere is. And it takes a lot of first looking at you've got variability factors, though, in there, like the sun going through an 11-year cycle of activity. So that's a change that's happening over short time scales. But then also what has to be brought in is the sun itself, tracking the behavior of the sun way back in time, and people who study that are able to feed into that because, yeah, it's a model, but that's something you couple into what's going on in the atmosphere right now, because you're right, what we're seeing right now is the rate things are happening right now, and then the shorter time scale changes with the solar cycle of activity over 11 years, but then those models going back to what the sun was like a long time ago, that has to feed in order to get those changes. And but certainly it also couples into what the other missions have found, that conditions were different, so that helps point the way also.
Liz Bowman, Twitter handle at elbowman007. In the 1960s, we were focused on the moon, and now we're focused on Mars. What do you guys predict we will be focused on in the future?
Mars.
We're a little biased up here.
And part of the reason we are studying Mars is to understand how Mars functions as a system, and hopefully MAVEN will help us answer that question. In 2030 or thereabouts, we want to send men to Mars, where we have a long-term goal to do something like that, and we want to understand how it is, so we can understand what we need to do when we send people to Mars and be able to have them survive. So those are, we want to continue to study Mars. Of course, we want to study other planets, but.
So, one of the things is that one of the reasons we have a Mars program is because Mars is one of the most easily accessible neighbors, right? And it has a rich history, and we think it looked like Earth at one point. So we can study Mars pretty easily. Every 26 months we can launch. It takes 6 to 12 months to get there, depending on how you design the trajectory and how big a rocket you use. And so it's not just a fascination with Mars, it's a fascination with our solar system, the evolution of the solar system, where we come from, where the solar system is going, how planets evolve. And so the Mars Science Program is bigger than it is a stepping stone to humans to Mars as well, and where we're going as a human race, but it's also bigger than that. It's the bigger question of the solar system evolution and planetary development. So there are a number of other places in our solar system we want to study. There are all kinds of amazing and fascinating places. If your question is where do we think we'll send humans, and Mars, it was a flip answer, but it's true. Mars is hard enough for robotic spacecraft, and the challenge of sending humans there is going to be a fascination and a lot of effort between now and when we do it, and an ongoing effort once we've made that commitment. So it really wasn't as flip as it sounded. But scientifically speaking, there's a lot of other interesting things. The answers we get at Mars can help us formulate questions for other destinations.
And even a better understanding Mars and the rest of the planets in our own solar system kind of feeds into, you've probably heard of the growing area of exoplanet research. We're seeing planets around other stars, too. And are there other Marses? Are there other Venuses? We're finding all kinds of other strange situations in other star systems. And so let's learn about what's in our own backyard. Maybe that will help us to interpret what we're finding further away.
I have a real quick question for Kelly. Working for NASA, it's a two-part question. Working for NASA, I got asked a lot if you believe there's life elsewhere in the galaxy and the universe, and I always used to reference methane on Mars as possibility there was. How'd you feel when the Curiosity results came off about methane, and do you think is there possible that something on MAVEN will contradict the fact that there's no methane on Mars? What's your take there?
Well, that's not something that MAVEN is addressing directly. They're not going to be looking for methane. Yeah, it's true. When Curiosity measured in situ, right there, methane, it didn't find a significant, a measurable amount, only upper limits. Whereas other techniques from ground-based telescopes a few years back mapped methane, and so it's. Personally, I'm still kind of waiting to see what happens, because it's and it's certainly something that scientists love to argue about. Was that like a one-time release of something under the surface? Because at first it was thought maybe this is something that would happen seasonally on Mars, but so far that hasn't been seen. And actually what Curiosity has seen, in a sense, is consistent with what's been seen from the ground, because that hasn't been measured again. So I'd say the jury's still out on that, but it's not one of the things that MAVEN is targeting.
But it's a methane sensor.
That's true. Yep.
Assuming a successful Mars orbit insertion and turning on of that methane instrument, maybe Mom will answer some questions, but MAVEN doesn't have the sensor.
Hi, I'm Sydney Swanson. I tweet at sydneyswanson.com, and this question comes from some 9th grade science buddies of mine in Eugene, Oregon, and they want to know, and please answer this any way that's appropriate from where you are, what level of error, what margin of error is allowable when launching a rocket?
Wow, that is a difficult question. The answer is there isn't much. It's hard to quantify whether we're talking the directions that we're going, the timing of the sequences. There's a lot that goes into it, and we work out to a lot of decimal places, and we've gotten pretty good at it, but it is still a very difficult thing to do, and unfortunately I don't think I can give you a solid answer, but the answer is not much.
When it comes to collaboration, outside collaboration on MAVEN mission and other missions moving forward, where do you all see the delineation of roles between federal and commercial space programs? And essentially, what can commercial space companies help you do that you can't do or you haven't been able to do yet?
You're all looking at me. So there are a bunch of answers to that, but primarily we look at our commercial space partners to come up with innovations primarily in process. I mean, we're the government, right? And we have a lot of process because we're answerable to a lot of people, like all of you and everyone listening and watching. And a company can take some risks in process and coming up with their own way of doing things. That's really important for us to be able to take advantage of. So you look at, for example, we use the neighbors down the street at Slick 40, right next door to where MAVEN's launching, the SpaceX folks. I mean, they definitely have their ability to pick a niche and go for it in a way that is focused and a process outside of our requirement. The other thing is we really like private and government partnerships. We've done a lot of different models of that, and one of them actually, MAVEN, is the result of one of those, in kind of, not in a partnership way specifically, but the role of government in enabling industry for us to take risks and enable industry to do new things. So Mars Reconnaissance Orbiter was a new thing, and it was a big, expensive mission that we invested in because that's, taking that risk, the scientific risk and the technology risk. And now it has become a way of doing business for our spacecraft partners. So there's kind of a mix there between, taking business risks and process risks and things where we're not providing oversight and checking in and making them do a lot of bureaucracy. And there's also the technology risk where the government does things that industry can't see a business model for. And it's two ends of the same spectrum, and there are a lot of applications for that we're going forward with.
And I know this is not going to answer the question directly, but it goes the other way, opposite. But in terms of MAVEN and the partnerships that we formed, we went for what has been almost true and tried. Instruments have flown in other missions before, not together. This is the first time that all of these instruments, payloads, are flying together. But we went for things, technologies, and aspects that had been tested before, and we stuck to the requirements and stuck to people and partners that had been in the business before, and that is one of the reasons why we have been so successful at sticking within the budget and sticking within the cost of the mission. If we had gone, developing technologies right off the bat, there would have been problems, and I'm sure that we wouldn't be here today.
And I just want to add a little more to my answer, too. So, for example, the cargo resupply for station, that's something that is becoming I can't. The word routine is a silly word to use when you're talking about anything that has ginormous amounts of explosives underneath it. That's not routine, and it never will be. But it is something that is known, and so that's kind of where I was going with the process risk. Is that these companies that are sending cargo, they're sending Cygnus, they're sending Dragon to resupply the station. These companies can sort of take that process risk on something that we know. What our role is to do the unknown as the government. We're to step out there, and there's a business to be made out of going back to station and doing it better and cheaper and in innovative ways. But there's a different business, and that's the business the government's in, of saying the huge technological risk of going beyond the Earth orbit, for example. And that's where it really requires us to step up and invest in those capabilities. Smaller example of which being MRO, being an investment in Mars orbiter capability. That has then been applied, and it's been applied to Juno and Grail and MAVEN. So that's kind of the break between the known and the things that you couldn't make a business model out of because you have no idea how it's going to turn out.
Hi, Jen Vargas, Twitter handle Jen Vargas. Very clever. I have a question for you.
At least you use your name. I just went with initials.
There you go. You're clever too. Question for you specifically, Lisa. Two-parter, very short. One, how has your glass experience been so far? And two, does it directly or indirectly affect MAVEN?
Answer to the second part is it doesn't affect MAVEN whatsoever, except for my teammates look at me and go, what is that thing on your head? Is that a mirror for your bike? So if I had glass I would use Google Glass to help more women take up biking because I bike commute. And I do take a lot of really great videos and narrate them. I actually have some from when I was down here in September and I rode from the Hilton up through the Air Force side to commute to work because I can bike commute in D.C. Why not here? It's only 20 miles each way. And I have some really fun narration. The problem is I'm an iPhone user. So, Apple, Google, they aren't quite well connected yet. So my glass experience has not been the full glass experience. It's, almost enough to make me consider switching phones, but not quite. I'm hopeful the next iteration in a few more months. I mean, it advances quickly. I don't even know how many OSs I've gone through on these since I got them. Yeah, it's on 11. Now we're at the Nigel OS. Come on, there's not a single Spinal Tap fan in the entire room.
Whoa. We have time for one more question.
Hi, it's John Ramsey. I'm at John Ramsey 33 on Twitter. Talking a little bit about the human aspect of Mars exploration in the coming years. I guess a question I had, are the folks over in HEO giving you specific requirements or things that they would like to learn from the mission as they get more intentional now as we're leading up to a human trip to the planet?
God, that's a great question. I got 3 answers, and somebody remind me if I only hit 2 of them. Because I tend to talk. First, the Mars program, through the Mars Exploration Program Assessment Group, has 4 goals, and we look for research about life, Mars climate, Mars geology, and preparation for humans. So our science program has always had those 4 goals for Mars in the Science Mission Directorate, since you're familiar with our directorates, obviously. So it's always been woven in there. And our partners in the Human Exploration and Operations Mission Directorate, or HEO, as he mentioned, they have had their strategic knowledge gaps, the things that they need to know before in preparation for sending humans. And so we work with them. They come to our assessment group meetings, and we work with them very well. But, it's always a matter of who doing a lot with not enough. And so what gets the most attention within each directorate's budget and planning. But for the Mars 2020 rover, which was announced last December that the next Mars mission NASA is funding is going to be a rover based on Curiosity, and it is going to do in situ astrobiological research with carefully selected samples and science instruments, but it's also going to advance our progress towards sending humans. So that announcement of opportunity is not just science instruments, but it's payloads, and it includes the opportunity for proposals for technologies that are relevant to human exploration of Mars. And so both the Technology Directorate and the Human Exploration Directorates have participated in developing that announcement. and will participate in the selection of payloads that will go on that rover.
Thank you. Let's give a round of applause to our panel. Lisa, Kelly, Sandra, and Chris. Thanks for joining us. Our next panelists are going to discuss the launch of MAVEN on Monday. We have with us Mick Woltman, the Vehicle Systems Engineer for NASA's Launch Services Program, and Joseph Fust, who is a Spacecraft Integration Engineer for United Launch Alliance. Thank you, gentlemen.
Afternoon. Everybody get to go on the tour this morning? Got to see some of the hardware out of the ASOC? Yeah. Well, we're going to continue on somebody's question earlier that asked about government and commercial stuff. But first of all, I am Mick Woltman, a Vehicle Systems Engineer with the Launch Services Program here at Kennedy, known as LSP. We boast a roster of engineers that specialize in rocketry and space integration. And part of our job, as was alluded to by the previous panel, is that once a spacecraft is selected, part of our job is then to go out and select a launch vehicle. In this case, United Launch Alliance's Atlas V for the MAVEN vehicle that we're all here for. So, but as part of that, as we get closer to launch on Monday, the NASA team also works with our ULA counterparts to look at the vehicle design, vehicle engineering, manufacturing, hardware review, make sure everything's ready, working up to the launch on Monday. That's a big part of our job in oversight as a government agency. And like I said, it's a close relationship we do with our ULA partner here in moving in. So let me just give you a couple quick things, and I'm going to let Joe talk about the vehicle processing. But this is the 41st Atlas V for ULA. It's the 10th Atlas V launch for NASA, and we're very, very proud of that and being able to continue working with our ULA partners on a successful mission here on Monday. For that. The vehicle configuration is a 401, if you're not familiar with that. The 401 is a 4-meter fairing, no solids. Somebody asked me that this morning. There are no solids on this vehicle, and a single-engine Centaur. With that, I'm going to let Joe talk a little bit about vehicle processing.
Okay. Thank you, Mick. So my name is Joe Fust, and I'm from United Launch Alliance. I'm in spacecraft integration, and so we work really close with LSP. In processing, probably they started the spacecraft started 10 years out, and LSP got involved a few years after that, and so I've been heavily involved. ULA has been heavily involved with LSP and the spacecraft customer for the last 5 years to get to this point. We've been talking about launching this a few years out, 2 years out, a year out, and now we're launching Monday. So that's a long time coming. So
we're excited about that, by the way.
With that, I want to show you how we got there. And just recently, we launched 11, 12 rockets a year, and this is the next one up, the next mission. And so we usually get our launch vehicle for the next mission before we launch the one before it. So the Delta Mariner came into port, and it had an Atlas V in it and the Centaur, both the booster and the second stage. And if you can go to the next picture, you'll see us pulling the Atlas out. We just use it as a regular tractor trailer and pull it out of the boat. It's parked up at Port Canaveral, and so the next shot. And here's the Centaur. It's bagged. Keep it clean. Keep the engines clean in the back, and you can see off on the right-hand side. The booster headed on the way too, and we go into the south gate of the Cape and end up over at the ASOC, the Atlas Space Flight Operations Center. Next shot. You can see it on its way. And once we get to the ASOC, it looks a little strange there, but this is the bottom half of the rocket, and there's a display outside the south gate.
Joe, the Delta Mariner comes from Decatur?
Decatur,
where
yeah.
the vehicle's
yes.
manufactured, correct?
Thank you. Yeah, out of Decatur and down the river, down into the Gulf and around the Florida Straits and up into Port Canaveral. Next chart. So eventually, that tractor trailer parks the Atlas V booster in the high bay, the Atlas Space Flight Operations Center. And that's where we park it there and do some horizontal processing. We do initial power on. We hook up the umbilicals to the side of the booster and the Centaur, which sits on the side. I'll show you a picture of that coming up here. Next chart is the back end of it. We actually connect into just beneath this pod here, hanging off on the bottom, and we will connect in our avionics, booster avionics pod harnesses. You can see the nozzles for the dual chamber single RD-180 engine, the business end. And the duct on the outside on the very top, that's the liquid oxygen feed duct. The LOX tank is on the top, and the RP1 tank is on the bottom. Next chart. So that's the Centaur. That's our second stage, and that's sitting catty corner to the booster. That's also connected connected electrically with harnesses. And in essence, we run through our first initial power on in this configuration. The first and second stage aren't physically touching each other, but that doesn't matter for the launch control computer. It thinks it's all connected, and we do our first power up and make sure everything's okay. It's real easy to be able to replace a box or any components when it's sitting in this configuration. As you start stacking it, it becomes harder and harder to get to some areas.
We jokingly refer to that as the smoke test, right?
The smoke test, yeah.
Don't let the smoke out of the boxes.
Yeah, that's right. First initial power on. So next chart. I'll stand this way a little bit too. So in order to put the first and second stage together, there's an engine at the bottom of the second stage, so you'll need interstage adapters. They're basically open-ended barrels, top and bottom. And you can see that this transitions from the booster diameter to the Centaur diameter. The Centaur is a smaller diameter than from 12.5 to 10 feet diameter. And so you can see the conical portion of that. So that's our GSE that's around in the ASOC high band. When we go to start bringing that stuff out to the VIF for vehicle erection, we bring the booster out first, then the interstage adapter, then the Centaur, and then the boat tail on top. And I think I might have a picture of the boat tail, the next chart. And so you'll see that right here. So a 4-meter payload fairing needs to, again, expand up to 4 meters. So the Centaur being 10 feet diameter, we need to come back out again. So we call this section here, we call that the boat tail. So those are the major components of the launch vehicle, minus the spacecraft, which is over in the facility being, at this time when we're doing all this, being processed and ready to be encapsulated. Next chart. So this is the day that we started booster hoist and connect to the MLP at the launch head. So we come out really early. One, we don't have to deal with the traffic if we start at 3 o'clock and 4 o'clock in the morning. And usually the winds are a little bit less earlier in the morning too, around sunrise. So the booster is placed at the base of the MLP, and we have an overhead bridge crane on the top that'll pick it all up and place it in. Next chart. So this is a view from the top of the building. You can see the booster laying horizontal, bottom, and we're about to start with this operation. Next chart. So there we are in mid-hoist.
This is the beginning of the MAVEN mission, right?
That's right. This is nobody else's booster. This is the MAVEN booster. So you can see the crane on top picking up the forward end, and we take this fixture on the bottom. We drive that in close to the MLP as we're picking up, so everything goes perfectly vertical. And next chart. And you can see us now. We're removed from the fixture at the bottom. They had pivots on it, and we removed it, and we're going to place it inside the VIF and on the launch heads. And there's 3 launch heads it sits on, and that align so that the vehicle is sitting straight up. Next chart. And there it is sitting on its launch heads. That big piece of steel at the bottom, just on the other side of the platform handrail, is one of the launch heads. It's sitting on 3 of those. All right, so when we place the vehicle there, we bring our decks around so we can work on areas and get ready for the interstage adapter, and we can actually physically touch it and line it up and put all the bolts around in the circle. So next chart. So the interstage adapter is already up. I didn't show any pictures of that. And so here's the second stage, the Centaur. It's getting ready to go up, and we do it in a similar fashion. Next chart. And there's the other picture similar to before, and it's getting ready to go. Next chart. And so we lift this one from the front end of it rather than the other end around. It's just a little bit different, but very similar. And its pivot point is here at the back end where the Centaur, or the RL-10 Centaur engine is. And next chart. And so it's already up and into the tower, and we are lowering the stage down in. There's people guiding it into the decks, into the hole in there, getting it ready to go into the interstage adapter, ISA. Next chart. And that's what it looks like from the other side of that deck. This guy's getting ready to receive the Centaur RL-10 engine, proven engine from a long time ago. Many upgrades to it, but it's still the proven RL-10 engine. Next chart. So at the same time all that's happening, the spacecraft is being processed, and this one over at the PHSF, where it had gone through many tests since it got down from Goddard. Since it got in from Denver. Lockheed Martin in Denver, and everybody came in from Goddard and LM in Denver you can see them all in there doing the processing. They had, I'm sure they described the solar rays unfurled and all of the components put back onto the main body of the spacecraft. Anyway, so at this point in time, everything is ready to go. All the covers are on. It's fully fueled, and we're getting ready to put the ULA payload fairing around and encapsulate it around. We use this GSE to hold it really tight because the payload fairing is kind of flexible. So you have to use a torus ring structure to give some rigidity to it, to put everything, to encapsulate everything together.
So I was going to say, your job here is in this picture is to pick out the 4 panelists from previously. You can't find them?
No.
Never mind.
Not hardly. Not hardly. Okay, next chart. So now we're fully encapsulated, and we're getting ready to leave the PHSF. Again, we do that really early because we want to get into the Air Force Station side and into the VIF before the traffic hits and before the wind starts picking up a little bit after sunrise. So we roll at 3:30, 4 o'clock in the morning. We get prepared for that. And actually, I think we rolled this one about 12 or 12:30 or so, something like that.
We don't do anything on a normal timeline.
No, we don't. So we're getting ready to roll out here. You see we're encapsulated, and this tractor trailer, I think if you go to the next chart, it has its own ECS system because we need to keep the ECS going on around the payload fairing, keep that air conditioned. It doesn't want to get to the Florida's moist air. Plus, we have special instrument purges on it as well, and so we have all K bottles and all the supply on for the trip and some. We have plenty of backup for that. So next chart. A little grainy, but this is the encapsulated assembly, the spacecraft encapsulated at the base of the MLP. There you can see the booster in back, and it's being connected to the hoist and getting ready to hoist and put up on top of the launch vehicle. So it's still pretty early in the morning. Next chart. So a little bit after sunrise, and we're already hoisting away, getting ready to put the spacecraft up. This is the entire spacecraft inside here. It's being hoisted obviously from the top, and there's guy wires coming down around the torus ring at the bottom, which is supporting the spacecraft and the payload fairing through a set of torus arms and H couplers and all that. So all is being supported. The payload fairing is supported separate from the spacecraft itself. 2 different load paths. So next chart. So we're almost up in there. You can see the guidelines. Everybody's controlling so we make sure that the wind doesn't take hold of the spacecraft and move it in. So everything's nice and tight on the way up. Next chart. And you can see we're almost there. To the time that we lifted to time this is here, it was probably about 10 o'clock or so, and 10:30 in the morning from when we started about 11 o'clock the night previous. So. And we have the rest of the day to fix it all up. So we're done usually about 9 or 10 o'clock. It's a 24-hour day for us.
Yeah, so this goes down, as Joe was saying, this goes down. They get really close, within a couple inches, and then they get a couple lining pins, line up, and then how many bolts go in around, roughly? Maybe not. 60 plus, maybe. Yeah. There's just a lot of bolts that go in there. So it is a long day after transport.
And I'll explain something. So the first thing that happens is the payload adapter on the spacecraft actually touches the front end of the Centaur, the launch vehicle first. And that's the standard EELV interface. That's 121 fasteners to hold that in. And once that's bolted up, then we lower the payload fairing the rest of the way. There's still a bit of a gap. It's still a foot.
Yep.
So in the encapsulated assembly portion, when they did it back at the PHSF, the payload fairing is actually sitting about a foot higher than it really normally would be. And so that's our process to do that. And so at the very bottom, you can see that boat tail area that I had pointed out when it was over when I pointed out over the ASOC, right? So that's the top end of the rocket and getting ready for the payload. So next chart. And this is what it should look like.
That's what we hope for on Monday.
Right. So between those two, we did after the launch vehicle is stacked, we do a bunch of combined system testing, integrated system testing once the spacecraft is mounted to it, and everybody's happy with all the data. And when we get to this spot right here.
So yeah, as part of that, as I said, the government agency LSP and ULA, when we do a lot of that testing after spacecraft mate, not only the ULA engineers but the LSP engineers, we review all that data. There's a lot that goes through. We report back to the panel that you saw previously, who's our spacecraft customer. And once we're all happy with that, we get to this point today where we go out to rollout, which I think a lot of you got to see this morning, and then get ready for launch on Monday. A lot of what Joe talked about, I think most of you have this or may have gotten this. The processing of the vehicle and stuff. There's actually a little cartoon in here that talks about that, how it gets from Decatur to the launch site, and then goes through a lot of this for processing the vehicle. So I was going to say I'll open it up for questions.
I think we have time probably for 2 questions, and the first one is right over here.
Hi, my name's Tony Rice. Question's for Joe, and it's specific to launch commit criteria for weather. Wanted to know if it certainly varies by vehicle, but does it vary by mission?
Yes, it does. Mostly, it varies by the launch vehicle we have. If we have a 5-meter fairing, there's more sail area. If we have solids, we lose some steering authority. This is our most steerable vehicle. It has the least amount of sail area, and we don't have any solids to worry about taking away from the RD-180 steering authority. Getting through that, and that's most of the weather commit. As far as the payload itself, it's got to go through the same atmosphere. Every single payload, whether it's going to a low Earth orbit or going up to Mars or anywhere in between. That's most of the weather criteria.
Right. We have launch commit criteria for the spacecraft also that has to be analyzed during the pre-launch countdown that the NASA launch manager and the engineering team will look at and then report back to the ULA launch director. So not only weather, but also vehicle commit criteria that has to have, and that does change depending on what's going on with the spacecraft bus and things like that.
I'm Kelly with the Commercial Spaceflight Federation. So first of all, congratulations on your 100% mission success with Atlas V.
Thank you.
It's really amazing. And my second question for you is if you could speak at all to the future of Atlas V as a reusable, reliable rocket for Boeing and Sierra Nevada's future, like Dream Chaser, for example.
So we're well on our way. You can speak to that too.
I was going to say first correction is it is a reliable rocket.
Yes, I'll get there. Very reliable.
And will remain that way.
That's right. So we've already been doing a lot of work and working with CST-100, CST-100 and Sierra Nevada's Dream Chaser. Matter of fact, tomorrow, as that vehicle is out there, we're actually going to do some survey work and planning on where to build extra swing arms and towers. And so that's been in the planning phase for a long time, and lots of PowerPoint charts, and that's all nice. But if we want to start cutting steel, we need to know exactly where some things are. So we're at the stages where we're actually getting some hard data to be able to build those structures. That's but a few years off. We're over on our other rocket program on the Delta side. We're going to, at the end of the year, next year, we're launching that. The Lockheed version of the capsule, right?
EFT-1.
Yeah, EFT-1. Yeah. So it's a manned capsule. It's going to be nobody in it, but that's in preparations and helping NASA out to prove that capsule. So ULA, both vehicles are well on their way to proving that out. So.
And you're going to hear a little bit more about that later on from our folks at GSDO. But Joe and I had a bet coming up here, and you did ask the first human spaceflight question, so.
Oh, you got it. You took it. I didn't realize you took it. Yeah.
We have time for one more question in the front.
Quick, so there may be time for one additional one. Just want to find out, is that photo sequence available online anywhere, or can it be?
So I'm able to show those photos. In order to be able to put them out to the outside world, each one has to be looked at by our global trade controls. So the lawyers have to look at it. So
I can answer that from the NASA side. Is if you go to nasa.gov through the processing of MAVEN, there have been approved processing photos through the MAVEN launch processing. Then you can get it off the media site that's run by NASA there. That's gone through ULA and NASA approval.
Yeah, there's a plethora of photos. You just can Google search anything and it'll bring it right up.
Thank you. Let's get a round of applause for Joe and Nick. Thanks, gentlemen. That was awesome. Don't know what that's about. Our Our next speaker is here to talk about the ongoing future missions on Mars, both human and robotic. He knows a little something about human spaceflight. He's an astronaut of 5 missions, and he is now the Associate Administrator for Science at NASA headquarters, John Grunsfeld.
Hello. Wait, hold on. I gotta get a picture of all you so I can tweet it. You having a good time? Yes. I drove by the Atlas V on my way over here. I couldn't resist. And I've spent a lot of time down here at the Kennedy Space Center driving around, and a lot of familiar feelings as I drove by. And I was looking around to see if maybe I could sneak up to the spacecraft and climb aboard and maybe hitch a ride, but it'd be awful short. But someday we will, hopefully very soon. So let me ask right off the bat, how many of you would like to go to Mars? Okay, I'll tweet that in a moment. How about the moon? Yeah, sorry, I should have raised my hand for Mars, too. We're on our way. Hopefully Monday, MAVEN will be a step in that direction. And, I got really excited by the results of the Curiosity rover. Basically, when it landed and it found that it was sitting in an old stream bed, freshwater stream. John Grotzinger said, yeah, if you were there, then you could drink the water. Because instantly, I had this view of Mars with running stream, clouds, snow-capped peaks, glaciers, like Earth. Mars was a happening place. A lot of that water is still there. We don't know whether life started on Mars or not. What drives me every day is trying to get to the answer, are we alone in the universe? And Mars is one place where life might have gotten started. The disappointing thing is it was probably about 3 billion years ago. But that's okay. MAVEN will figure out what happened to the atmosphere, at least give us pretty good clues. Mars has always had such a special place in human history. Just dreaming about Mars, inventing, war stories about Mars, not so good, but, it's a red planet, and for whatever reason. And people have dreamed of life on Mars, and now we may be able to figure out if there is life on Mars, if life ever existed on Mars, with our suites of missions. So we have Opportunity and Curiosity on Mars. We have Mars Odyssey and Mars Reconnaissance Orbiter. We still have only mapped at the highest resolution using the Mars Reconnaissance Orbiter camera a small fraction of the surface of Mars. And I encourage you to go on the website and look at all these pictures, because Mars is really a beautiful planet, amazing things that we've seen. Getting back to some of the things we've seen when Phoenix landed near the pole, and we were wondering whether we would find water, ice, and the thrusters blew off the dust and we landed on a glacier. But we also saw snow on Mars. And so even though Mars may have been nice like Earth 3 billion years ago, I kind of think it's not that bad now. A lot of people go to Antarctica to do research. I like to go up into the mountains, high mountains, and live on glaciers with half an atmosphere. Now, getting down to less than 1% of an atmosphere is somewhat problematic, but that's what we have spacesuits for. And I love being in a spacesuit, so I don't see that as a problem. But we have MAVEN. Then in 2016, we're launching the InSight mission to Mars. It's going to be a lander like Phoenix, and it's going to be a geophysical monitoring station. We've looked at Mars surface in a great deal. We've got the orbiters. MAVEN will examine the atmosphere, but we haven't looked inside of Mars yet. And so the InSight geophysical station with a seismometer and a heat flow experiment will be looking into Mars. And you might say, well, Mars isn't really geologically active the same way the Earth is. Are we going to see any Mars quakes and other things? And the answer is we probably will. It's a relatively big planet, and Mars also gets hit by meteorites. And when Mars gets hit, it'll ring, and we'll hear that, and we'll be able to map the inside structure and then determine the heat flow through the surface. which also will give planetary scientists a view inside. In 2016 and 2018 also, we're partners in the European Space Agency ExoMars program. They have an orbiter and then a lander in 2018. And we're very excited by the 2020 rover, which will be the chassis, similar to the chassis of Mars Science Laboratory Curiosity, but with new instruments. And we just put out an announcement of opportunity to select the instrument suite for that. Very likely it will have a caching system. So as it finds the really interesting rocks and minerals, it will put them into little containers. And then in some future flight, hopefully we can either get those back robotically, or perhaps some person will go and grab them and bring them back. So that'll launch in 2020. I think we're going to go to Mars. A lot of the stuff we're working on at NASA, the International Space Station, is designed around Mars, our planetary exploration program. But it's not just about Mars for science. As you all know, we have a spacecraft orbiting Mercury, Messenger. We have a lot of spacecraft around this very strange planet that's incredibly hard to understand, that's called Earth. One of the thrusts for the science program at NASA is to try and determine if there's intelligent life on Earth. And with the Earth science data we're getting about the atmosphere and changes in the climate, the jury is still out on that one, most definitively. We have quite a few spacecraft and plans for exploring Mars. The Juno spacecraft is on its way to Jupiter. We have Cassini at Saturn. And we have New Horizons on its way to Pluto. So I think the next few years, the next 3 to 4 years, are going to be an incredibly exciting planetary science program, including Mars. But of real excitement is 2018, we launched the James Webb Space Telescope. And it's going to be able to do amazing things in solar system science, and of course all the rest of the universe, in case anybody would be interested. But for Uranus and Neptune, the real opportunities to study the weather patterns, for instance, on Neptune, which I think is very exciting. And so we have quite a lot queued up. Last 2 weeks, I made the slowest circumnavigation of the world I have ever made. And I actually don't know, some of you may know, but I don't know how many times I've orbited the Earth in approximately 92 to 96 minutes. But it's roughly 1,000 times. This one took me 2 weeks with very strange stops. I stopped in Nepal and in Thailand, and this was associated with our Earth Science program. And what I found in both places, and they're very different countries, obviously, but different economic levels, different issues, is that NASA is extremely popular, and the NASA science that we do is extremely popular around the world. And so I found that energizing. On the other hand, I'm jet-lagged right now. It's the middle of the night for me, so I'm a little bit tired. But what I'd like to do now is open it up for questions, and maybe that'll stimulate a little bit more discussion.
Start over here, only because it's closest to me.
Hi, I'm Kat at Kat Robinson on Twitter. What mission would you like to see besides human missions? We all want to see humans on Mars, humans beyond Mars. Is there something that you would really like to see science-wise, like within our own solar system, not necessarily Mars? Like, what's something that you just think would kind of really give us new insight?
Well, the quest to try and find out, are we alone in the universe? So when I was growing up, I used to lay in the grass at night. I wasn't allowed to watch Star Trek when it first came out because it was an adult show, adult themes. And you got to remember, this is, we had just gotten our first color television, and kids weren't allowed to watch TV unless the parents allowed them to, and all this kind of thing. But I was allowed to see the space missions. So I distinctly remember Gemini and Apollo. Mercury, I was a little too young, and that inspired me. But the first run of Star Trek I couldn't see, but by the time I was 12 or 13, I was watching it in reruns. So I would lay in the grass and look up at the stars and wonder, are there any planets around those stars? Is there anybody else out there? How many people have done that? Okay, so the hands that didn't go up are from young people who live in cities and they don't know there's stars out there. That's a shame. But I used to do that all the time. Well, just last week or the week before last, we saw the Kepler results. Pretty definitively, every star or nearly every star you see in the night sky has at least one planet or a solar system, whole solar system. If it has one, it probably has more. Solar system around it. And somewhere around 20-30% have a rocky planet, many in the habitable zone. And so the odds are that there are a lot of Earth-like planets out there, meaning rocky planets between maybe 3/4 of the size of Earth to twice the size of Earth, where liquid water could exist on the surface. Maybe 10 to 40 billion in our own galaxy alone. That's a lot of cool planets. Now, that means there's places we can go, not in our solar system, but really compelling. But in our solar system, there are really only 2 planets that we can probably live on, but that doesn't mean that there aren't more places that microbial life could live. And so I think a mission to Europa would be really exciting. Oh, wait, we haven't done it yet, so I'm not going to take any applause. But I think a Europa mission would be really exciting. But Europa is really tough because it's bathed by incredibly intense radiation, by the magnetic field of Jupiter accelerating charged particles. So it's not an easy place to go. And I think Titan is a place we ought to examine a little bit more. Titan is probably the most like Earth in our solar system in that it's a large moon, but a large body. It has an atmosphere. It has lakes. It has rivers. It has mountains, canyons. They happen to be hydrocarbon lakes. On the other hand, living in Houston, we had hydrocarbon lakes too. So, and smog and other things that we share with Titan. But there are organics. There's energy, and there's carbon. And those are the 3 key ingredients for life. So who knows? There might even be life on Titan. It's a little bit cold, but for the chemistry, but certainly there's lots of chemistry. But there's enough organics there that it's an interesting question, an interesting place to look. So I think the moons and icy moons of the gas giants are places we really should go investigate. And we are. We have Juno going there. But I'd like to see a Europa mission in the future and some other icy moon missions. All of these are very difficult. But we have opportunities for those in our Discovery and New Horizons programs. And a manned mission to Mars. I would really like to get some astrobiologists and planetary scientists on the surface. That's the first step.
My name is Van, Van aka The Rock on Twitter. What do you think about the Mars One program that's looking to send people to Mars by 2023 with no intention to bringing them back?
Well, when I look at our NASA inventory of technology and the ability to so I don't know very much about the Mars One program or for that matter, Inspiration Mars. I think, for a mission where you want to bring people back, I think we need about 20 years of serious, work towards that mission to do it successfully. Now, my background, of course, is space shuttle missions, Hubble Space Telescope repairs, where we get one chance and we don't want to blow it. If you're willing to take enormous risk, there's lots of ways to do things that would be a lot faster. But personally, if I were to go to Mars, I'd want to have a high probability of being able to live there for a long time. And I don't think by 2023, we'd be able to develop and refine the technology because, so another thing I like to do is, as I mentioned, high-altitude mountaineering. And you have to carry everything with you. So you can't take, too much stuff. So when I climbed Denali, which is in Alaska, Mount McKinley, I took 120 pounds of food and stuff with me. And that's a lot. That means carrying about half of it in a backpack and half of it in a sled. And we tried to, a team of 5 people, we tried to bring as much stuff as we could so if something went wrong, we'd still survive. And one of the goals was to come back. The level 1 requirement, for those of you who follow that kind of thing, was come back with all your fingers and toes, not climbing the peak. That was secondary. That was the fun part. Well, I don't know how much fun, but it was exciting. It was a lot of work, and it was fun once we got to the top. So, you know, if all you want to do is sprint to Mars and then die, it's not that hard, right? But I mean, who wants to do that? I mean, you'd want to go and explore, right? So I don't, you know, what I find exciting, really exciting, is that Inspiration Mars, you know, Mars One, you know, all these different groups want to go to Mars, and that they would be willing to do it as a one-way trip, that it's that interesting. Ultimately, and I don't know what time scale, I think we should send people one way because I think colonizing Mars is important. You know, I think it was John Young, Captain John Young, who one of my heroes, flew Gemini, Apollo, and Shuttle, 6 missions, may have coined this theorem, but I've adopted it. Single planet species don't survive. It's a theorem. We don't want to prove it. You know, the dinosaurs had their own demonstration. But ultimately, we need another planet to live on. And ultimately, if we want to survive long-term, we need another solar system to live in. That's why the Kepler results and the ground-based observatory results are so exciting. There are other places we could go. But we need, you know, interstellar space flight first. Now, Voyager is in interstellar space. You know, so we can do that long-term. But, you know, I think there's recognition and growing excitement, you know, that Mars is within our reach. We just have to decide, you know, to aggressively go in that direction. And, you know, NASA's making a lot of efforts in that direction.
Thanks. We have time for one more question.
Hi, this is a perfect follow-up question. My name is Patrick Ford. My Twitter handle is Patrick Martian, or @PatrickMartian. First of all, I just wanted to...
You're going to ask a moon question?
No.
Oh, okay. Sorry.
First of all, I just wanted to say it's such an honor to get to meet you. You're one of the people that really inspired me to become an astronaut. And I think it's really funny because I'm actually one of the 3 or 4 people in the room that's actually signed up for the Mars One mission. So my question to you is, what's the one attribute that you think is the most important to have as an astronaut faced with obstacles or disaster or challenges on a mission?
You have to like to fix things, I think, which is another way of saying be a jack of all trades. You know, it's important to, you know, especially if, you know, if you're going one way, you want to know as much as you can about human physiology and how to fix humans. That's not to say you have to be a medical doctor. You know, I think wilderness emergency medical technician is probably a lot closer. But, you know, the key is going to be able to improvise and to fix things along the way. People talk a lot about, oh, we have to make systems that will run continuously for, you know, n years, where n is, you know, 1 or 2 or 5 or 10. It's more important that you build systems that can be maintained and fixed than that have to run continuously, because things break. And a love of exploration. I think certainly for Mars One or any Mars trip, if you want to go, how many of you saw those cruise ships in the Canaveral port? If you want to go on a cruise ship, you're going to have to wait a long time. If you want to rough it, you know, then you can go earlier. And I think it's that tolerance of adversity. If you thrive in adversity, you know, then, you know, these kind of sprint trips and roughing trips will appeal to you, and you'll do well. You know, if you don't like adversity, you know, then space flight's probably not for you. So, yeah. All right, I'm going to ask one more time. Who'd like to go to Mars? So, there's still a few hands that aren't going up. But.
Dr. Grunsfeld, thank you.
Thank you very much. So I'll ask one more question. Are we going to launch on Monday?
Yeah.
All right. Enjoy the launch.
Our next speaker is from here at Kennedy Space Center. Is going to discuss the ground systems transformation going on. His name is Chad Brown. Thank you, Chad. Sorry about that. There's just 2 people.
Slight change in plans. Hi, my name is Chad Brown. I work here at Kennedy Space Center. Like was previously mentioned, I work for a Ground Systems Development and Operations Program. We're one of 3 programs based here at Kennedy Space Center. The other 2, as you're aware, of Launch Services Program and Commercial Crew. GSDO's primary mission is to transform Kennedy Space Center into a modern launch facility. And to do that, we need to think sort of out of the box. One thing that we've done in the past with Kennedy Space Center, when launching the Space Shuttle and launching the Saturn V, we've launched one vehicle configuration and family. So what Kennedy's going to invest in is a multi-user facility. So with Saturn V, you saw that you brought in the Saturn V launch vehicle. Platforms went to one location to use. The mobile launcher used certain pads. That's the only vehicle you can launch. Space Shuttle, same thing. Platforms went to one location. You only had access to that. You only launched on that one mobile launcher and that one pad. You couldn't bring in, say, a Delta II, Atlas V, things of that nature. So what we're doing is modifying the VAB, the pad, and our facilities to accommodate other next-generation launch vehicles. Our primary, our anchor tenant is SLS, as you can see here in the backdrop. But we're not limited to just SLS. If you take a look at our platforms, many of you went to a VAB today. I'm assuming they took you to a High Bay 3 and you saw the crawler transporter. If you take a look at the High Bay 3, those platforms that you saw are modular. They go up and down. They go to different station locations. The superstructure for those platforms can accommodate inserts. Those inserts, as the OML of the launch vehicle changes, whether it's a commercially procured vehicle or an SLS vehicle, we can just simply change out inserts. So if one of you guys hits the world Powerball and decide to start your own startup and bring a launch vehicle out here, GSDO can accommodate your launch vehicle. Not only with the mobile launcher, but the pad itself is a clean pad, very similar to what you see on the ULA Atlas V pad. There are no fixed service structures at the pad. It's clean. So we bring our mobile launcher. Right now we're using a Constellation. We reuse the Constellation mobile launcher. We're modifying it to accommodate SLS. SLS mobile launcher is unique to SLS. It's adjustable as the launch vehicle evolves. When it comes out to the pad, we just simply interface with the mobile launcher, not the vehicle. So if you win your Powerball, start your own business, bring a launch vehicle out, we've got a couple extra MLPs. You can simply just mate to the MLP we take out, and you can launch for that pad. You don't need to invest in an extra pad. SLS. So as SLS evolves, and I'm not going to steal any of Kimberly's thunder here. Try not to, at least. As it evolves and goes with liquid boosters, or it goes with upper stage or a Block 2, we can simply adjust our infrastructure with the VAB and the mobile launcher. The mobile launcher, we can adjust the crew access arm, the GSE arms, and we call our umbilical arms GSE. So that's one way we're doing that also. Did y'all have an opportunity going to the LCC today? I'm not sure if that was on a tour or not. So the LCC, if you go back in history and take a look at what they did for the Saturn V program, we had approximately 400 plus people sitting on console. While on console, they launched the vehicle, monitor it. Shuttle program, we had about 300 people. For SLS, our primary tenant right now, or our anchor tenant, we plan on having only 50 people on console, with the goal of only 25. So we're pushing the limit. We're really trying for it. SLS is slated for Firing Room 1. So on 2017, when we're going to launch our first SLS launch vehicle, we have Fire Room 4 that's modular. It can set up with 4 different firing or monitoring rooms, if you will. So if you want to have a social during 2017, you could sit in the fire room potentially and watch it. Or if our guys want to send something to a distant planet and they want to send in and monitor their spacecraft in LCC, we have that available. I'm not going to take most of the time here. I'm going to yield the remaining time to Kimberly.
Okay. All right. Well, my name is Kimberly Robinson. I'm from NASA's Marshall Space Flight Center that's in Huntsville, Alabama, a few miles north of here, as you know. It's the home of the original rocket scientists that built the Saturn V that took men to the moon several decades ago. I have a doctorate in engineering, but I think what is more important is that I have a real passion for space exploration. And I think that may be something we share. I was very excited to see all those hands go up about who wants to go to Mars. That is wonderful. That's exciting. And the Space Launch System, as Chad's been talking about, the SLS, this is the rocket that can get you there. So it was just a few short years ago, 4 years ago as a matter of fact, that I was here and watched a rocket known as Ares 1X launch from Pad 39, right out those windows. At the time, it was named Time Magazine's Invention of the Year. And I would say with this new rocket that we're building, I would personally consider it the invention of the decade. So, looking back, in February of 1962, John Glenn became the first American to orbit Earth. President Kennedy, who always had a way with words, in a statement afterwards said that space is the new ocean, and I believe the United States must sail on it and be second to none. And for a number of years, we've had an exciting shuttle program, but we've stayed relatively close to shore. So, we're about to head back out into deeper waters, into an area we like to call deep space. To do this, we need a great new ship, a rocket ship, to sail the oceans of space. The Space Launch System, or SLS as we call it, is this great new ship. It's comprised of 4 space shuttle main engines, which I don't know if you know, but they had basically 100% reliability through 135 shuttle flights. It's a pretty incredible engine. It has 2 extended solid rocket boosters, state-of-the-art avionics, and it's going to be constructed using the most advanced manufacturing techniques we have. It will be the most powerful rocket ever built, with 10% more thrust off the pad than the enormous Saturn V. It will tower over us at 321 feet tall. Think about it. That's like launching a 30-story building into space. It will be capable of carrying the Orion spacecraft with up to 4 souls on board. It will also continue to evolve to carry massive amounts of cargo. It will be capable of launching an entire space station in a single flight. That's something that took more than 30 launches and more than a decade for us to launch and build the space station. Imagine what this new capability will do for us. We'll be able to travel to destinations in record time. John Grunsfield was talking about the icy moons of Jupiter. We can launch a probe to Jupiter and arrive in less than 2 years, whereas today it takes almost 7. And it will be versatile to travel to many islands in the ocean of space, including asteroids, the moon, Lagrange points, and Mars. So why do we want to build this new rocket? We get that question a lot. Well, first of all, we are explorers by nature. We want to see what is around the next corner. We want to test the boundaries. It inspires us and compels us to try harder and reach further. Along the way, we will make new scientific discoveries. We will develop new technologies that will enhance our lives in the future. And also, we will develop the toys and the tools for tomorrow. And we will create future job markets for all of us. When the first American satellite was launched in 1958, I'm sure no one could have imagined that 50 years later, we would have almost 1,000 satellites in orbit around our Earth, sending us cellular phone signals, weather data, and global positioning information every second of every day. So who knows what this next age of exploration will bring? I certainly don't. But a feat this large requires the skills and the capability from people and businesses across this great country. NASA is harnessing these talents together for a single focused purpose: to build a great ship that will be an engineering marvel and will push the reaches of humans in space beyond what we've ever done before. So we're here today observing and celebrating the MAVEN mission to Mars, which we hope will start on Monday. Why go to Mars? We've heard some of this. Robotic precursor missions are necessary to understand the present and past history of Mars. Mars is our new world. The red planet is our closest planetary neighbor. It shows signs of abundant water and atmosphere in the past. It could hold the secrets of life in our solar system. So in a few short years, SLS is on schedule to launch from here on pad 39B, right outside those windows. The first launch will be unmanned to test out all the systems. The first mission will propel the Orion spacecraft around the moon and back. Then in 2021, SLS will fly the Orion with a crew of 4 astronauts on board to orbit the moon and return safely, perhaps to rendezvous with an asteroid. After these initial shakedown flights, we'll be ready to aim for Mars and extend human presence into our solar system. So we're glad you're here today. We ask for you to be part of this journey. Join us as we prepare for this trip. You can find us on all the social media outlets, Facebook, Twitter, Instagram, Flickr, for instance. Let people know that for 1/2 of 1 penny of a federal tax dollar, we can change the human experience and open up new worlds with programs like MAVEN and SLS. With imagination, resourcefulness, and determination, we will take ourselves to new heights to explore our vast and wonderful universe while creating a better life here at home. Thank you.
I think we have time for one quick, very, very quick question. Our broadcast time is about to expire. Anyone?
It's John Ramsey at John Ramsey 33. So I'm also from Alabama. So proud to be from the home of Rocket City. I've got a question for Kimberly. First of all, congratulations to you and Todd and Gary for passing PDR. With flying colors. I guess the question would be, Decision Point C, and everybody may want to know what that is coming up. When do you expect that to happen, and what obstacles do you see between now and then?
Well, we are very busy preparing for that. Our KDPC, for those that don't know about it, that's called Key Decision Point Charlie, or C. That is where we move from formulation into implementation. And that's a major milestone for any program. For our program, it means that basically the agency commits to us within a certain schedule and budget range that they will fund the program and they wish for it to go forward. So that's very big. It will happen in early December. We will get the ruling from the agency. And so that's when we feel that we are truly christened, if you will, to go forward as a ship. So we're very excited. We are very hopeful and optimistic. We think that we have done a wonderful PDR, a very clean PDR. It's not technical challenges that hold us back. It's just whether this country has the national will to go forward and to continue to invest in space. We hope they will.
Kimberly, Chad, thank you very much for joining us. That is going to conclude our broadcast. Remember to tune in on Monday at 1:28 p.m. Eastern Time for the launch of MAVEN. And remember, if you see something really cool like launching to Mars that NASA's doing, share on Twitter and Facebook and Google+, or just walk over to your neighbor and tell them about it and share the exciting work we're doing here at NASA. Go MAVEN. Thank you for coming.